So good day, ma'am. I am Hasim Madris, and now I'm going to discuss the chapter 7, which is the first order circuit. So, source free RC circuit or source free resistor capacitor circuit. So, source free RC circuit occurs when its DC source is suddenly disconnected. So, the energy already stored in the capacitor is released to the resistors. Just like as you can see in this figure 7.1, this is what we call the source free RC circuit. So our objective is to determine the response which for pedagogical reasons, so we assume to be the voltage across the capacitor. So since the capacitor is initially charged, then we can assume that the time t equals O, the initial voltage is V multiplied by 0 is equal to V sub O. So with this corresponding value of the energy stored in a capacitor, work is equals to 1 half CV squared. So by applying the KCL at the top node of the circuit, we have the current in capacitor added plus the current in resistor is equals to 0. So by definition, I sub C is equals to C derivative of V with respect to T, and I sub R is equals to V over R. So thus CVC dV over dt is equals to VR equals to plus VR is equals to 0. And dV over dt is equals to by um, cross multiplying it, we have the dV over dt plus V over RC is equals to 0. So integrating both sides, we can get the integrate the dV over dt and plus V over RC. We can get the ln of V equals to negative T over RC plus ln of A. So by simplifying it, we can get the ln V over A equals to negative T over RC. And taking powers of E produces V of T is equals to A E raised to negative T over RC. So, but from the initial condition, V0 is equals to A and A is equals to V sub O. So hence that V of T, V multiplied by T is equals to V sub O E multiplied by E raised to negative T over RC. So this just shows that the voltage response of the RC circuit is an exponential decay of the initial voltage. So as you can see in this figure 7.2, so this is the voltage response of the RC circuits. Next is the natural response of a circuit refers to the behavior, so in terms of voltage and currents, of the circuit itself with no external sources of excitation. Next is the rapidity. The rapidity with which the voltage decreases is expressed in terms of the time constant, denoted by the lowercase Greek letter tau. So the time constant of a circuit is the time required for the response to decay by a factor of 1 over E or 36.8% of its initial value. So it means that this is simplified as the at T is equals tau. So V sub O multiplied by E raised to negative tau over RC. So it equals to V sub O multiplied by E raised to negative 1 is equals to 0.368 V sub O, or simply tau is equals to RC. So in terms of constant, that in terms of constant, Vt is equals to V sub O multiplied by T, and it is raised to negative T over tau. Tau is equals to RC, right? So we can change RC by the Greek letter tau. So this is the values of Vt. Divide V sub O negative equals E raised to negative T over tau. If we have the time of tau 0.366788, we have 2 tau, 3 tau, 4 tau, or 5 tau. Okay, that's all. So with the initial voltage in equation 7.9, we can find the current as I sub r is equals to V over R, and is equals to V sub R, V divide R, E multiplied by E raised to negative T divide tau. So we can get this, the power dissipated in resistor, this one, of V for various values of the time constant in this figure 7.4. So next is the energy absorbed by resistor up to time t is work is equals to integral of 0 with the initial value of 0 and t. So power is equals to Vi, and I is equals to Vr. So we can change P or power into V squared divide R and multiply by E raised to negative 2 divide tau. So it is equals to tau V squared negative 2R multiplied by E negative 2 divide tau, and we can insert substitute the value of the initial value and the final value of time. So we can get 1/2 CV squared close and open parenthesis 1 minus E raised to negative T sub T divide tau. So tau, as we remember, RC is equals to tau. So as you notice this one, that T is equals to infinity, and work in the work in resistor, energy stored in resistor is infinity. So therefore, 1/2 CV 1/2 it is equals to 1/2 CV squared, which is the same as the work in capacitor. So the energy the energy initially stored in the capacitor. So the energy that was initially stored in the capacitor is eventually dissipated in the resistor. The key to working with a source-free circuit is finding the initial voltage across the capacitor and the time constant tau. So that is for the RC circuit. This is for example. So if in figures shown below, so let the voltage in capacitor is equals to 15 volts, and we're gonna find the V sub C, V sub X, and I sub is for T is greater than 0. So as you can see in this circuit, the solution for this one is solve for the resistor in circuit, which gives us, we have the 8 and 12 which is in series, so we could add that 1 by 20, and 20 and 5 is now in parallel, so we can solve for the equivalent resistor, which is equals to 4. So since we have the total or the equal resistance of 4 ohms, so we know the equivalent circuit after combining the series parallel circuit. Time constant is equals to tau is equals to equivalent resistance of capacitor equals to 4 multiplied, since we have the 4 ohms, multiplied by the capacitor of 0.1 farad, and we can get the time of 0.4 second. So thus V is equals to VO E multiplied by E raised to negative T over tau. So we have, since we have the the voltage of 15 multiplied by E raised to negative T, we have, and we have the 0.4 of time V. So the voltage of the capacitor is equals to V is equals to 15 15 E raised to negative 2.5 T. So we can use the voltage division in finding the V sub x. So V sub x is equals to 12. Since we have the 12, divide by 12 plus 8. So we can get the we can get the 0.6 multiplied by 15 multiplied by 15 time multiplied by 15 e raised to negative 2.5 t, and we can get the value of the v sub x as 9e raised to negative 2.5 t. So finally, the value of the since I is equals to VR, so Ix is equals to Vx. Since we have the value of R as 12, so we have the Rx of 12, and it is equals to, we have the value of Rx of 9e raised to negative 2.5. We simply divide that by 12, so we can get the 0.75 e negative 2.5 raised to negative 2.5 t. So in source free RL circuit, so in this circuit, RL is a resistor inductor circuit. So our goal is to determine the circuit response, which we will assume to be the current through the inductor. So we select the inductor current as the response in order to take the advantage of the idea that the inductor current cannot change instantaneously at t is equals to O. So we assume that the inductor has an initial current of I sub O, or simply it's quite the same as the capacitor. It is I multiplied by 0 is equals to I sub O. So with the corresponding energy stored in the inductor, the energy storage in conductor, we have this formula as 1/2 Li squared. So applying the KVL around the loop, we have the V sub L and V sub R. It is equals to 0. So it means that L di over dt is equal plus Ri is equals to 0. So, or simply if we cross multiply that, we have the di over dt plus R over L multiplied by I, so equals to 0. So rearranging the terms and integrating it, we can get this one. The integral of with the initial value of I sub O and I t di over dt is equals to negative integral and the initial value of 0 and final value of t r over L dt. So by integrating it, we can get the ln of I, and we have the initial of I sub O and final of IT, and same in the right side, we can get the final answer of ln I over t IT divide I sub O is equals to negative R multiplied by t divided by L. So taking the powers of E, we have the I equals to I sub O E raised to negative RT divide L. So in the time constant for the resistor inductor circuit, tau is equals to L divide R. So as you can see in this, so thus it means I is equals to IO multiplied by E raised to negative T divide tau. So in that, we can find the voltage across the capacitor as V sub R is equals to I sub IR, and or I sub O multiplied by R E raised to negative T divide tau. So the power dissipated in the resistor is equal to P equals to V sub R multiplied by I equals to I squared I sub O squared multiplied by R E negative 2 divide tau. So the energy absorbed by the resistor is, we can get this formula. So as you remember, in inductor, tau is equals to LR, where in the capacitor, tau is equals to RC. So should be note that the difference between the value of tau in the inductor and capacitor. So note that as t equals to infinity, in the work in the resistor in inductor is equals to 1/2 Li squared, so which is the same as the work in inductor. The initial, which is the same as the initial energy stored in the inductor, as in equation 7.14. Again, the energy initially stored in the inductor is eventually dissipated in the resistor. And the last is the key to working with a source-free resistor inductor circuit is to find the initial current I sub O through the inductor and the time constant of the circuit. So we should note for that there's a difference between the value of tau in capacitor and inductor. So this is for example. Assuming that the I/O equals to 10 ampere, so calculate the IT and IX in the circuit shown. So first we use the mesh analysis, something like I can, yes. We have the two. We have the 2 I sub 1 minus I sub 2 plus 1 is equals to 0. So we can get that I sub 1 negative I sub 2 is equals to negative 1/2. Have the first equation, and 6 I sub 2 negative 2 I sub 1 minus 3 I sub 1 is equals to 0. So it means that I sub 2 is equals to 5 over 6 I sub 1. So we can calculate for that the value of that. So hence the equivalent resistance is equals to RTH, and RTH is equals to V divide I is equals to 1/3 divide 1/3 ohms. So the time constant is L over R, right? So we have the L of 1/2 and the equivalent resistance of 1/3. So we can get the time constant as 3/2 seconds. So thus the current through in the inductor is equals to 10e raised to negative 2 divide 3 ampere. So in method 2, so we may directly apply QL to the circuit as in figure B. For loop 1, we have the 1/2 di over dt plus 2 multiplied by I sub 1 minus I sub 2 is equals to 0. So simply d over dt plus 4I sub 1 minus by 4I sub 2 is equals to 0. So for loop 2, we have the 6I sub 2 negative 2I sub 1 negative 3I sub 1 equals to 0, or simply I sub 2 is equals to 5 divide I sub 1. So substituting equation 7.3.4 into equation 7.3.3 gives us di over dt plus 2 divide 2/3 I sub 1 equals to 0. By rearranging the terms, we have the di over I is equals to negative 2/3 dt. So since we have the I sub 1 is equals to I, so we may replace the I sub 1 with I, so then integrate. So substitute I sub 1 by I and integrate. So we have the ln I, we have the initial time and final time is equals to negative 2/3 t. We have 0 on t, ln. So by integrating it, we have the ln it divide I 0 is equals to negative 2/3 t. So taking the powers of E, we finally obtain that obtain the I is equals to I0 e negative 2 raised to negative 2/3 t. And by that, we can get the value of I as with a time greater than 0, we can get 10e raised to negative 2/3 t. So the voltage across inductor is measured by using this formula. The V is equals to the L di dt. We have the 0.5, we have the L of 10, multiplied by negative 2/3, e raised to negative 2/3 t. So you can get the negative 10 3 divided 3 e raised to negative 2/3 t. So since the inductor in the and the 2 ohms resistor are in parallel, we can solve for the Ix by V divide 2. So since the Rx, R sub x is 2, so we can, and we get the value of V by dividing it into 2, we can get the negative 1.6667 e raised to negative 2/3 t. So example 7.4. So the switch in the circuit shown has been closed. The switch in the circuit has been closed for a long time at t is equals to 0. So and then the switch is open. So calculate the I sub t, it for t is greater than 0. So since we have the this circuit, first we find the I sub 1. So when t is less than 0, then therefore the switch is closed. And the inductor acts as a short circuit in the DC circuit. So the 16 ohms resistor is short circuited. Then is short circuited. The resulting circuit is shown in figure A. To get I sub 1 in figure A, we combine the 4 and 12 ohms in resistor in parallel. So the 4 and 12 resistor is now in parallel. So to get the resulting equivalent resistor of that, we have the 4 times 12 divided by 4 plus 12. We can get the 3 ohms. So hence I sub 1, we have the 40 I is equals to VR again. So we have the voltage of 40, we have the 2 and 3 ohms. So we can add that one because they're in series. So we can get the I sub 1 as 8 ampere. So we obtain I from I sub 1. So in figure A, using the current division. So since the current through an inductor cannot change in time instantaneously, then therefore I0 is equals to I0 raised to negative is equals to 6 ampere. So in other terms, when t is greater than 0, the switch is open and the voltage source is disconnected. So we now have the source free RL circuit. So combining the resistor, we have the equivalent resistor of, since 12 and 4 is series, so after we get the value of by adding that one, it is now in parallel with 16 ohms. So in that we can get the equivalent resistor of 8 ampere. The time constant is, as again in inductor, the tau is equals to LR. So we have the inductor of 2, we have the equivalent resistance of 8. So by that we can get the time constant of 1/4 seconds. So thus IT is equals to IO e raised to negative t divided tau. So we can get the 6e raised to negative 4 t ampere. So now let's go for singularity function. So singularity functions, we can say that it is a function that either discontinuous or have continuous derivatives. So singularity functions also called as switching functions. So it is very useful in circuit analysis. This serves as a good approximation to the switching signals that arise in circuits with switching operations. So there are three most widely used singularities functions in circuit analysis: the unit step, the unit impulse, and the unit ramp functions. So the step function ut is 0 for negative values of t and I, and 1 I think. For positive values of t, we can get this figure is what we call the unit step function. So in accordance to the mathematical terms, ut, it means that the time o, the 0, is when time is lesser than 0, and 1 u, the value of u is 1 if the time is greater than 0. So the unit step function is defined as t is equals to 0, where it changes abruptly from 0 to 1. So it is like dimensionless, like other mathematical functions such as sine and cosine. So as you can see in figure 7.23 depicts the unit step function. So if the abrupt change occurs at t is equals to t sub o, where t sub o is greater than 0, instead of t equals to 0, then the unit step functions becomes u is equals to t minus t sub o. So we can get 0 as t is less than t sub o, and if 1, then therefore t is greater than t sub o, which is the same as saying that the u is delayed by t sub o seconds. So as we can see in the shown in figure 7.24, to get equation 7.25 from equation 7.24, we simply replace every t by t minus t sub o. So if the change is at t equals to negative t sub o, then the unit step functions becomes u is equals to t plus t sub o. So in that way, if the value of t is 0, then therefore t is less than negative t sub o. And if it is 1, then therefore the t is greater than negative t sub o. So figure 7.24. So the unit step functions delayed by t sub o. Then in B, the unit step advanced by t sub o. So use the step function to represent an abrupt change in voltage or current. So like the changes that occur in the circuits of control system and digital computers. For example, in voltage. So if the value of voltage is 0, then therefore the t is less than t sub o. And if we have the vt of v sub o, then therefore the t is greater than t sub o. So it may be expressed in terms of the unit step functions as vt, then therefore vt is equals to v sub o multiplied by u t minus t sub o. So if we let t sub o is equals to 0, then therefore the v of t is simply the step voltage of v sub o u. So as we can see, so its equivalent circuit is shown in figure 7.25. So it is evident in figure 7.25 that terminals A minus B are short-circuited, so V is equals to O again. For t less than 0, and that V is equals to V sub O, it appears at the terminals for t is greater than 0. Similarly, a current source of I sub O is shown in figure 7.26, while its equivalent circuit is in figure 7.25. But notice that for t less than 0 is an open circuit. I is equals to 0, and that I is equals to I sub O flows for t greater than 0. So as you can see in figure 7.25 A and B. So if you can see like this figure, we can call that voltage source of V sub O T. And in the figure B of 7.25 figure, it is equivalent circuit. 7.26 in figure A, this is what we call the current source of I sub O. And B is the equivalent circuit. So the unit impulse function is 0 everywhere except at T sub O. T equals 0. So it is undefined. So the derivative's unit step function is the unit impulse function, which we write as in T is equals to d over dt. So derivative of the u. So since u of t is like this one, so if we have the value of 0, then therefore t is less than 0. So if the u of t is undefined, then therefore t must be equals to 0. And 0, if we have the 0 again, then therefore t is greater than 0. So the unit impulse function shows that the delta function is shown in 7.27. So this is what we call the unit impulse function, or simply known as the delta function. So the unit impulse may be regarded as an applied or resulting shock. It may visualize a very short duration impulse of unit area. So this may be expressed as this one, mathematically 0 to raise to negative, 0 raised to positive, t of dt is equals to 1. So let's say, for example, an impulse function of 10 t has an area of 10. In figure 7.28 shows that the impulse function of I o 5o multiplied by t plus 2 is equals to 10 t and 4 negative 4 multiplied by t negative 3. So this is what the impulse functions looks like in figure 7.28. So to illustrate how the impulse function affects the other functions, let us evaluate the integral. So as we can see here, the integral with the initial value of a and b, we have the ft t minus t sub o dt. So where a is less than t sub o, but t sub o is less than b. So since t minus t sub o is equals to 0, except at t equals t sub o, then therefore the integral is 0, except at t sub o. Thus, using this formula, we can get this one. Okay, so in this function, this shows that when a function is integrated with the impulse function, we can obtain the value of functions at the point where the impulse occurs. So this is a high useful property of the impulse functions known as the sampling or shifting property. So the special case of equation 7.31 is for t sub o in 0. So then therefore the equation 7.32 becomes like this one. Okay. So the unit ramp function is 0 for negative values of t and has a unit slope of positive values of t. So integrating the unit of step function results in the unit ramp function. So we can write this one as r of t is, with the integrating it by, we have the initial and final value of negative infinity and t. We have the u derived by deriving it, and rt is equals to 0. If 0 value of the rt, then therefore the t is less than or equals to 0. And if we have the t, it should be that t is greater than or equals to 0. So in figure 7.29, previously shows that the unit ramp function in general, a ramp is a function that changes at a constant rate. So this one, as you can see in figure 7.29, this is what we call the unit ramp function. So the unit ramp function may be delayed or advanced as shown in figure 7.30 previously. Okay. So for the delayed unit ramp function, if r multiplied by t minus t sub o, then therefore if we have 0, then t is equals or less than t sub o. And if we have t minus t sub o, t should be greater than or equal to t sub o. And for the advanced unit ramp function, r multiplied by t plus t sub o is equals to, if we have the 0, the t should be less than or equal to negative t sub o. And we have the value of t plus t sub o, then therefore t should be greater than or equal to negative t sub o. So in that way, we should keep in mind that the three singularity function, the impulse, state, and ramp, is quite related by the differentiation as t is equals to du over dt, or simply u of t is equals to dr over dt. So by integrating the both sides, we can get the u of t, and we can with the initial and final value of negative infinity and t, we can get the r of t with the, again, the initial and final value of negative infinity and t. We can get this formula. Okay. So in figure 7.30, as you can see, the figure in A is, this is what we call the unit ramp function, which is delayed by t sub o. And in figure B, this is what we call the unit ramp function, which is made by the advance by t sub o. So let's say, for example, in 7.6. So express the voltage pulse in 7.31 in terms of the unit step, then calculate the derivative and sketch it. So the type of pulse in figure 7.31 is called the gate function. So it may be regarded as a stem function that kind of something switches at one value of t, then switches off at another value of t. Then the gate function is shown in 7.31. So for example, we have the switches on at t equals 2 seconds, and after a few minutes or few seconds, it switches off at t is equals to 5 seconds. So it consists the sum of two unit function as shown in, as you can see a while ago in figure 7.31. So it is evident that v of t is equals to 10u multiplied by t negative 2, and subtract it by 10u of multiplied by t negative 5 is equals to 10u of t minus 2 and u of t minus 5. So taking the derivative of both sides, so this gives us dv over dt is equals to 10 t minus 2 negative t negative and negative 5. So as you can see in this one, in this figure, so as you can see in this first figure, which is figure A, so that is what we call the decomposition of the impulse. And in figure B of 7.31 figure, this is what we call the derivative of the impulse. Okay. So example 7.7 in 7.7. So express a sawtooth function in shown in figure 7.35 in terms of singularity function. So we have the solution. There are three ways in solving this method: by mere observation and other methods involving some functions. Okay. So we have the figure 7.36, the partial decomposition of v t in figure 7.35. So since v1 v sub 1 of t goes to infinity, so we need another function at t is equals to 2 seconds. So in order to get v of t, so we have this function like b function b v sub 2, so which is a ramp function of slope -5 as shown in the figure 7.36. So v sub 2 of t is equals to -5r t minus 2. So adding v sub 1 and v sub 2 gives us the signal in figure 7.36. So obviously, this is not the same as v sub t in figure 7.35, but the difference is simply a constant 10 units of t is greater than 2 seconds. So by adding the third signal, v sub 3, where v sub 3 is equals to -10 u t minus 2. So you can get that vt as shown in figure 7.37, substituting the equation is 7.7.2 through 7.7.4 into equation 7.7.1. So by substituting that, we can get this one. The vt is equals to vr multiplied by t -5r t minus 2 and -10 u multiplied by t minus 2. So this is what we call the complete decomposition. So in method 2, in figure 7.37, so a close observation of 7.35 reveals that v of t is a multiplication of two functions, so a function and a gate function. So that gives us vt multiplied by ut -u minus u of multiplied by t minus 2. After that is we can get the final answer of 5r of t, -5r multiplied by t minus 2 -10 u multiplied by t minus 2. The same as before in method. So the same as before in method 3. It is quite like similar to method 2. So we can also observe from the previous previous one in figure 7.37 that v of t is a multiplication of ramp function and a unit step function as shown in figure 7.38. So in figure 7 in method 3, thus gives us vt is equals to 5rt multiplied by u, and it is being multiplied by -t plus 2. So if you replace the u of negative t by 1 minus ut, then we can replace the u multiply by -t plus 1 plus 2 by 1 minus u t minus 2. So hence we can get a resulting equation of 5rt multiplied by 1 minus u, since we replace the u by 1 negative u. Okay, so t minus 2. So this can be simplified is the method as in the method 2 to get the same result. So another topic, we're now in the step response of RC circuits. So the step response of a circuit is its behavior. The excitation is the step function, which may be a voltage or a current source. So considering the RC circuits shown in figure A, this one, which can be replaced by the circuit shown in figure, where v sub x is constant voltage source. So that is one. So you can see in this figure, that is shown as the complete response of the RC circuit to a sudden application of DC voltage source. So assuming the capacitor is initially discharged, if we assume that the capacitor is uncharged initially, was it V sub O is equal to 0. So in that way, in that way, Vt, we can get if if its value is 0, then therefore the t must be less than 0. And if V sub x multiplied by 1 negative e raised to negative t divide tau is if the time should be greater than 0, or Vt is equals to V sub x multiplied by 1 minus e raised to negative t divided by tau. Okay. So the current through the capacitor is obtained using I equals C over dV over dV over dt. So we can get that I equals CV of dV over dt. So it is equals to C divided tau V sub multiplied by C V sub x e raised to negative t divided tau. So since we're talking about the capacitor, okay, so tau is equals to RC, and time should be or must be greater than 0. So I equals to Vx over R e raised to negative t divided tau. So rather than going through the derivation above, there is like systematically approach, or rather a shortcut method for finding the step response of an RC or like simply RL circuit. So complete response is equals to natural response stored stored energy plus the forced response or the independent source, or simply V is equals to Vn plus Vf. Okay, so where Vn is equals to V sub O e raised to negative t divided tau, and Vf is equals to V sub s multiplied by 1 negative e raised to negative t divided tau. So the natural response, simply or in what we call the transient response, is the circuit's temporary response that will die out with time. So the forced response, or like the steady state response, is the behavior of the circuit a long time after an external excitation is applied. The complete response of the circuit is the sum of the natural response and forced response. Therefore, we can get this formula. In the forced response and the steady state response, the Vt is equals to V multiplied by infinity plus Vo minus V multiplied by infinity with e raised to negative t sub t divided tau. So thus finding the step response for an RC circuit, this requires the three things. Okay, this one, the first one is the initial capacitor value, which is V0. Second is the final capacitor voltage, which is V multiplied by infinity, and the time constant tau. Okay. So say for example in example 7.9, the switch in figure below has been in position A for a long time at time is equal to 0. So the switch moves to B, determine the V for t is greater than 0, and calculate its value at t equals 1 second and 4 seconds. So if we have this circuit, the reason for this one, so for t less than 0, the switch is at position A. So the capacitor acts like an open circuit to DC, but V is the same as the voltage across 5 kilo ohms resistor. Okay, in this circuit. So hence, the voltage across the capacitor just before t equals to 0 is obtained by voltage division. So voltage division, we have the 5, since we are going to, they have the same voltage. So V is equals to 5 plus 3 multiplied by 24, we can get the O raised to negative by 15 volts. So using the fact that the capacitor voltage cannot change instantaneously, VO is equals to VO raised to negative is equals to VO raised to positive. So it means they have the same value of 15 volts, okay? So 40 greater than 0. The switch is in position B. The Thevenin resistance then therefore is connected to the capacitor of RTH. So it is equals to the RTH there is 4 kilo ohms, okay? And the time constant is since we are talking about capacitor, so tau is equals to RC, okay? So we have the RTH of 4 times 10 to 3 since it is kilo ohms, so that will be raised, that will be times 10 to the negative 3 multiplied by 0.5 times 10 to the negative 3, okay? So in that way we can get the value of time constant by 2 seconds, okay? So since the capacitor acts like an open circuit to DC at steady state, V infinity is equals to 30 volts, okay? So after that we can just like substitute the value of this one by using this formula. So after that, if at the time is equals to 1, we can simply just substitute the t as 1. After substituting it, time is equals to 1, we can get the 20.9 volts. And if the time at 4 seconds, we just simply substitute the 4 into t, and we can get the value of 27.97 volts at time is equals to 4, okay? So in example 7.10, so in figure below, the switch has been closed for a long time and is open at t is equal to 0. So find I and V for all time. So we're looking for I and V, okay? So for t sub O, t less than O, as less than 0, the switch is closed at 3 u of t equals to 0. So that the 30 voltage source is replaced by short circuit and should be regarded as contributing nothing to V, okay? So since we have the value close the 30 volts here, we should close circuit it. So we have the value of V as 10 volts, the I, we have the V, we have the VR since we're solving for R, the current of R, we have the 10 volts, the resistance of 10, and we have the voltage of 10. Since it is negative, so the current is negative 1 ampere, okay? So that is one. So this should be what it look like. So for t is greater than 0, the switch is open at the the 10 volts. 10 volts now, but 10 volts now is disconnected from the circuit. So 30 ut voltage source is now operative, the 30 voltage source. So the circuit becomes that shown in figure 7.46, and after a long time the circuit reaches steady state and the capacitor acts like an open circuit again. So you obtain V multiplied by infinity by using the voltage division. So writing V infinity is equals to 20 divided 20 plus 10 multiplied by 30. We can get the V infinity of 20 volts. So the Thevenin resistance of the capacitor's terminal, we can solve for the Thevenin since the 10 and 20 is parallel. So parallel with 10 is parallel with 20. We can get that 10 multiplied by 20 divided 30. So we can get the Thevenin resistance of 20 divide 3 resistance. So the time constant there is, as we can see, we can solve for the capacitor. We're solving for the capacitor. So the tau is RC, okay. So RTH multiplied by C. So 20 divided 3 multiplied by 1/4. So we can get the 5/3 seconds. So thus Vt is equals to V multiplied by infinity, and Vo is it minus is subtracted by V infinity e to the negative t divide tau. So equals to 20. So we simply substitute the value. So we can get the 20 negative 10 e negative 0.6. The raised to negative 0.60. So that is the voltage of that. So to obtain I again, let's say to obtain I, we notice in figure 7.46b that I is the sum of the current through the 20 ohms resistor and the capacitor. Okay, since the previous the one that I explained. So we have the value of I as V divided 20 and plus C dV over dt. So by substituting the value of that, we can get the current as 1 plus E raised to negative 0.60. So note from the figure 7.46, V plus 10I is equals to 3 is satisfied, okay. As expected, hence that V, the 10 volts, the value of V with 10 volts at as time is less than 0. As time is equal or greater than 0, we can get the 20 negative 10 E raised to negative 0.60. And in current, if we have the current of negative, if we have the time of less than 0, we can get the negative 1 ampere. And if the time is greater than 0, we can get the current of 1 plus E raised to negative 0.6. The 0.6. So notice that the capacitor voltage is continuous while the resistor current is not. Okay. So steps in response of, so we're now in RL circuits, RL circuits. So let the response be the sum of the natural current and forced current. So it means that I is equals to I sub n plus I sub f. So natural response always decaying exponential, that is, so In is equals to A E raised to negative t divided tau. So in inductor, the value of tau is L divided R, okay. Where is it quite different between in the capacitor. So capacitor is tau is equals to RC, wherein in inductor tau is equals to L divided R, okay. So the forced response is the value of the current for a long time after switch in figure A is closed. So the entire source voltage V appears across R. Thus, the forced response is IF now equals to V sub S divided R. So substituting the equation gives us I equals A E raised to negative T divide tau. So substituting the equation gives I equals AE raised to negative T sub T divide tau is equals to Vs divide R. So since the current through the inductor cannot change, IO raised to positive is equals to I0 raised to negative is equals to I sub O, okay. So thus at time 0, I sub O will now become A plus V sub S divide R. So from this equation, from that previous equation, we obtain A as A equals to IO minus 7 sub V sub S divide R. So substituting A, we get the I as V sub S R divide R plus or multiplied I sub O minus V sub SR multiplied by E raised to negative T divide tau. So I is now equals to I infinity plus IO minus I infinity multiplied by E raised to negative T divide tau. So thus, to find the step response of an RL circuit requires the three things, okay? Just remember these three things. So the initial first is the initial inductor current at time is equals to 0. The second one is the final inductor current. And the last is the time constant tau. So you should must learn the difference formula, the difference between solving the tau in inductor and capacitor. So if let's go back here. So if I sub O is equal to 0, then therefore if time is less than 0, then I is 0. If time is greater than 0, then I is equals to V sub SR divide R multiplied by 1 negative E raised to negative T divide tau. So we can get this formula. The voltage across the inductor is obtained from using V is equals to di over dt. Okay. So we get the V is equals to di over dt again. Okay. So we have the tau. So tau again is L over R. Okay. So if time is greater than 0, we're using this formula. Okay. This one. So let's have an example. So example 7.11, find I in the circuit below for t greater than 0. So assume that the switch has been closed for a long time. So we have this circuit here, where we have the solution. So the solution for that is when t is less than 0. The 3 ohms, so you can see the 3 ohms is short circuited, okay? And the inductor act like a short circuit. So the current through the inductor at time equals to 0 raised to negative is just before time equals to 0. Okay, so I 0 raised to negative is I, as you remember, I is equals to VR. So you have the 10 volts and the 2 ampere at 2 ohms. Okay, so we can get the I as 5 ohms, 5 ampere. So since the inductor current cannot change instantaneously, I raised IO raised to negative and IO raised to negative and positive for the other one is they have the same value of 5 ampere. So when time is greater than 0, the switch is open. 2 ohms and 3 ohms are now in series, so we can solve for that as I is equals to 10 divide 5, so we can get the resulting of 2 ampere. Okay. Then another, the Thevenin resistance across the we should solve for the Thevenin resistance for this one. Okay, so the Thevenin resistance across the inductor terminals is the total resistance for that is we had the 2 plus 3, so equals to 5 ohms. So the time constant for that is tau again is L over R, but we are using the Thevenin resistance of 5 and we have the inductor of 1/3. So if we multiply that one, I divide that one, we can get the 1 over 15 seconds. So that's using this formula, we simply substitute the givens as t greater than 0. Okay. After that, for t greater than 0, KVL must be satisfied. That is 10 equals to 5i plus the LdI over dt. So by solving for that, you can get this one, the 10. Okay. So I think we just need isa lang example. So that's all for chapter 7. Thank you.